In this video, we use the definition and Laplace transforms that we've already derived to find the Laplace transforms of the hyperbolic sine of kt, the hyperbolic cosine of kt, sine of kt, and cosine of kt. I will find the Laplace transforms of the hyperbolic sine and hyperbolic cosine of kt first, using these Laplace transforms that we discussed earlier and the linearity property of Laplace transforms. Remember that or of the Laplace transformation, if you are taking the Laplace transform of a times f of t plus b times g of t, it turns out that that's the same as a times the Laplace transform of f plus b times the Laplace transform of g. Or in other words, a times f of s plus b times g of s. We're going to use this along with this and the definition of the hyperbolic sine and cosine functions in order to find the Laplace transforms of hyperbolic sine of kt and hyperbolic cosine of kt. So let's do that. The Laplace transform of hyperbolic sine of kt is the Laplace transform of 1/2 times e to the kt minus e to the negative kt by definition of the hyperbolic sine of kt. The hyperbolic sine and hyperbolic cosine functions are defined in terms of exponential functions. Now, this is just a linear combination of exponentials, and we know the Laplace transform of e to the at from the derivation that we did in the last video. So we can factor out that 1/2 and then take the Laplace transform of each of these pieces separately. And I'm factoring out the -1 as well. We get this. The Laplace transform of e to the kt, according to this formula, a is equal to k, so this is 1 over s minus k, and here we're subtracting 1 over s minus a, where a is -k, so we're subtracting a -k, so that's adding k, and so we get that expression there. Now, if I get a common denominator, and that's typically done when we're finding the Laplace transform of the hyperbolic sine, it's usually just written as a single fraction. If I wanted to do that, I would multiply this fraction by s plus k over s plus k, and I would multiply this fraction by s minus k over s minus k. So I didn't really leave myself much space, did I? But this is 1/2 of s plus k over s minus k times s plus k minus s minus k over s minus k times s plus k. And if we distribute that negative there, we have minus s minus a -k is plus k over this s minus k times s plus k, which we know is s squared minus k squared. The s is reduced, and we end up with 2 k's in the numerator. We want half of that, so we're going to have a single k in the numerator. So the Laplace transform of the hyperbolic sine of kt is k over s squared minus k squared. So we have derived that formula just using the Laplace transforms of e to the kt and e to the -kt. Now, this was only equal to this provided that s was greater than a. So this really should only be equal to this when s is greater than k and s is greater than -k. Well, s will be greater than, well, it really depends on whether k is positive or negative. I guess we're assuming that k is positive here. If we're assuming that k is positive, when s is greater than k, s will also be greater than -k. So we can say this: the Laplace transform of hyperbolic sine of kt is equal to k over s squared minus k squared, as long as s is greater than k. Okay, so that's the hyperbolic sine of kt. Now, hyperbolic cosine is very similar. The only difference between the definition of hyperbolic sine of kt and the hyperbolic cosine of kt is that we're going to have a positive sign here instead of a negative sign. So let's work that one out. The Laplace transform of hyperbolic cosine of kt is equal to the Laplace transform of 1/2 of e to the kt plus e to the negative kt by definition. You can factor that 1/2 out and then take the Laplace transform term by term. The Laplace transform of e to the kt is just e, or 1 over s minus k. And then we're adding the Laplace transform of e to the negative kt. So that's 1 over s minus a negative k, so that's s plus k. And then I multiply this fraction by s plus k over s plus k. And I multiply this fraction by s minus k over s minus k. And watch what happens. Now we have the same denominator. So we'll have s squared minus k squared if we distribute. And then I'll have s plus k plus s minus k. The k's will reduce and we'll have 2s in the numerator. 2s times 1/2 is going to be a single s. And this is appropriate as long as s is greater than k and s is greater than negative k, assuming k is positive, and we do assume k is positive. This is the only condition that's required because, of course, k is less than negative k, which is less than s if this first condition is satisfied and we're assuming k is positive. So we have this second Laplace transform. The Laplace transform of hyperbolic cosine of kt is s over s squared minus k squared when s is greater than k. That's what we have right there. Okay, so we've got these two, and I'd really like to find the Laplace transform of sine and cosine of kt just by using Euler's identities. But I don't want to use that because we haven't really proven that everything that we are doing applies when this exponent is a complex number. We have assumed that we are working with real numbers the whole time, not with complex numbers. So let's say that we're not making that assumption. Let's just use the formal definition to find the Laplace transform of sine of kt now. Well, in that case, we have the integral from 0 to infinity of e to the negative st times sine of kt. You probably recognize this from calculus 2, where you've got that exponential times the trig function. You know, this is one of those integrals where it's a little tricky. You end up with the exponential times the trig function on both sides and you have to solve for it. Now, since this is an improper integral, the first thing we always do is we write it as a proper integral. So the issue happens at the upper limit. So we're going to take the limit as b goes to infinity of this expression right here. And then we'll evaluate this proper integral instead. Okay, and that requires taking the antiderivative of something that looks like that. So what I would do is I would use integration by parts and then not worry about this 0 and b at first. I would just focus on evaluating that antiderivative using integration by parts. And it actually really doesn't matter in this case what you choose to be the u and which term you choose to be your dv. Either one will work. So I'm going to let u be my exponential function and dv be everything else. So u is e to the negative st. dv is sine of kt times dt. And I'll have to differentiate to get du and anti-differentiate to get v. Well, the derivative of e to the negative st is the exponential function times the derivative of the inside with respect to t. And the derivative of a constant times t is that constant. And then don't forget to multiply by your dt. The antiderivative of sine is negative cosine. And if I were taking the derivative of that, I'd multiply by a k. Since I'm taking the antiderivative, I divide by k. Well, then according to integration by parts, the result is u times v minus the integral of v du. So we end up here. So I have this exponential times sine of kt. The integral of that turns out to be u times v minus the integral of v du. That's a negative times a negative. That's going to be a positive. Now, if I look at this as my u and all of this is my dv, and then I factor out that s over k, we can do this again. Actually, I think I'll let that all be my u this time. So we'll say u is s over k times this exponential. dv is cosine of kt dt. The derivative of this is this times the derivative of the exponential. So the exponential's derivative is the exponential times the derivative of the inside by the chain rule. So we're going to get another negative s out here. Don't forget your dt. And the antiderivative of cosine of kt is sine of kt times 1 over k. So we end up with uv minus the integral of v du again. And so I'm just going to call this I for integral, because that's what I'm looking for. And this is negative 1 over k times e to the negative st times cosine of kt minus s over k. Oh wait, no, I included the s over k in there. Minus the result of this integration by parts. We get u times v. So I have s over k squared times this exponential. Minus the integral of v times du. That du is negative, so we're going to end up adding there. And that k times that k is going to give me a k squared in that denominator. Do you see it? You end up with the same integral on both sides. You had this integral I on this side, and you end up with the same integral over here. I think I will distribute the negative and factor out that s over k squared. Or s squared over k squared. Okay, so this is my I. Now, if I'm trying to get I by itself, and I am, because I'm trying to evaluate this integral, I'll add this to both sides. So I'll have I times the quantity 1 plus s squared over k squared. If I add this to the other side and I factor out the I, and then over here, I'll have negative 1 over k times the exponential times cosine minus s over k squared times the exponential times sine. And if I want a common denominator, I'll write this 1 as k squared over k squared, so I end up with k squared plus s squared over k squared. And so if I'm trying to get I by itself, I will multiply by the reciprocal of this for each term. So I have negative 1 over k times the reciprocal of this. So that's k squared over s squared plus k squared times this exponential times cosine of kt. And I have minus s over k squared times the reciprocal of this again, times the exponential times sine of kt, and it was an improper integral, so I guess we should have a plus c. And we can reduce the k squareds there. We can reduce one of those k's there. And so we end up with this. I think I'll factor out the exponentials as well. So I've got e to the negative st times negative k over s squared plus k squared times cosine of kt minus s over s squared plus k squared times sine of kt plus c. Okay, so that was a lot of work, but just a little calc too. So we were able to evaluate this. And now we want to substitute in 0 and b and take the limit as b goes to infinity in order to get the Laplace transform of sine of kt. So it's the limit as b goes to infinity of this expression evaluated at t equals b. So I've got e to the negative s times b times this expression here. Replacing my t's with b's. And then when t equals 0, I will substitute 0 and this will be 0. So this guy will be gone. And then I'll have cosine of 0, which is 1. And then I'll have an e to the 0, which is also 1. So I'm just going to end up subtracting a negative k over s squared plus k squared. So it's going to be adding k over s squared plus k squared. You might be thinking, how do I evaluate the limit of this as b goes to infinity? Well, don't be intimidated by it. This is a constant as far as we're concerned, if we're taking the limit as b goes to infinity. So this is a constant times a cosine function, which is oscillating between negative 1 and 1. And this is a constant times a sine function, also oscillating between negative 1 and 1. And both of those constants are negative. It doesn't really matter because they're multiplying something that's oscillating. But these are all bounded, and then it's multiplied by this exponential function that's getting very close to 0. So if this is bounded and you multiply it by this exponential that's getting close to 0 as b goes to infinity as long as s is positive, then this product has to go to 0 as well. So this whole piece will approach 0 because this function is bounded and this guy goes to 0. It's like I'm taking something that's oscillating and then I multiply it by an exponential and it just sort of damps out. And this is approaching 0 as long as s is positive. So we have that the sine of kt is equal to this limit, which is equal to k over s squared plus k squared. So we have that limit, or that Laplace transform. The Laplace transform of sine of kt is k over s squared plus k squared when s is greater than 0. And I want to show you how similar that is to the rule that we just derived for hyperbolic sine of kt. See, with hyperbolic sine of kt, we got this. And that actually makes sense because those two denominators for e to the kt and e to the negative kt, it's an s minus k times and an s plus k. If I get a common denominator, I see an s squared minus k squared. Well, if I replaced this kt with I times kt, I would get something that's very close to the sine of kt. We'd have to adjust the constants as well. But we didn't want to do that. I didn't want to do that because I didn't want to make an assumption about whether we could substitute in complex numbers without proving that we could first. So we had to use the long way, calculus 2 methods, to avoid that proof. But now we're here, and it turns out that the Laplace transform of sine of kt looks a lot like the Laplace transform of hyperbolic sine of kt, and that's because sine of kt can be written in terms of complex exponential functions. We could do that using Euler's identity, which we have applied before earlier in the semester without deriving or proving or anything like that. So, and I guess that would be okay here, but I didn't want to do that this time. I wanted to show you where this comes from without using that fact that we still have yet to derive. Okay, so that's how we get the Laplace transform of sine of kt. I don't think I'm going to derive the Laplace transform of cosine of kt because it's basically the same idea. But the Laplace transform of cosine of kt is, by definition, the integral from 0 to infinity of e to the negative st times cosine of kt dt. So that requires writing it as the limit of a proper integral, and then evaluating this integral using the method that we just used for e to the negative st times sine of kt. So you'll see the integral on both sides, you'll add that to one side, you'll get the integral by itself, and then you'll have the antiderivative, and then you'll plug in b and plug in 0 and subtract. After you do all of that, I'm not going to do that this time, but you can do that if you want to. It's very similar to what we just did. You're going to find that this limit is equal to s over s squared plus k squared, as long as s is positive. So this this Laplace transform of cosine of kt is equal to this. Laplace transform of hyperbolic cosine of kt looks exactly the same, but instead of having an s squared plus k squared in the denominator, it has an s squared minus k squared. So now we've got 4 Laplace transforms, 4 more Laplace transforms to add to our list. We know that the Laplace transform of 1 is 1 over s. The Laplace transform of e to the at is 1 over s minus a. The Laplace transform of t to the n is n factorial over s to the n plus 1. That's true for n equals 1 as well. We get 1 over s squared in that case. And then we have the Laplace transform of sine and cosine of kt. And the Laplace transform of the hyperbolic sine and cosine of kt. Now, these last two can be found just using the linearity properties of the linearity property of the Laplace transformation and our knowledge of the Laplace transform of e to the at. And without making any assumptions about domain issues, we can derive this just using techniques that we learned in Calculus 2. And it turns out to look almost identical to that hyperbolic sine of kt, but it has an s squared plus k squared in the denominator. This is the only one we didn't prove. It looks almost identical to the hyperbolic cosine of kt, but it has an s squared plus k squared in the denominator. So notice that k is a constant. S is the variable, that's our transformation variable. Both the cosine and hyperbolic cosine have an s in the numerator. Both the sine and the hyperbolic sine have a k in the numerator of their Laplace transforms. And the sine and cosine functions have the s squared plus k squared in the denominator. And the hyperbolic sine and hyperbolic cosine functions have the s squared minus k squared in the denominator, which is just what you would expect if you were to have a linear combination of exponentials, e to the kt and e to the negative kt, and then you are adding them together and getting a common denominator. So now that we have this list, we can take the Laplace transform of expressions that look like that. So let's say we've got sine of kt minus t to the 6th plus hyperbolic cosine of 2t plus 4 times e to the t over 2. Well, then just applying these rules and using the linearity of the Laplace transformation, here k is 3, here n is 6, here k is 2, and on this term a is 1/2. So we'll take the Laplace transform of sine of 3t. That's going to be 3 over s squared plus 3 squared. Here you've got 6, or t to the 6th, so it's going to be 6 factorial over s to the 6 plus 1. And for hyperbolic cosine, you're going to have an s in the numerator, and s squared minus k squared. K is 2, so that's 4. And then we'll bring our 4 down here. And then we'll multiply by 1 over s minus a, where a is 1/2. And on this one, we might simplify by multiplying by 2 over 2 to get rid of that complex fraction. And I would probably simplify that 6 factorial as well, although that's one of the factorials that I don't know. Oh, 720. I should have known that. I could have done that if I thought about it for a second. That's okay. Let me get over here. And we get this, 2s minus 1. So this is the Laplace transform of that expression. And we can find that just by applying these rules. Since we derived these rules, we know exactly where they come from. They come from the definition. Now, if we were starting with an expression like this, we could go backwards as well using the inverse transforms. So the inverse transform of these 7 functions, or each of these 7 functions is each of these 7 functions. I'm not going to do that in this video. So I think that's it for this video. I'll see you next time. And maybe we'll do some partial fraction decomposition to compute some inverse transforms.